let's talk about the Orbit-Stabiliser theorem, which is all about group actions. So if we have a finite group G, so let G be a finite group acting on a set X. So for example, we might have a regular dodecahedron and it has a group of rotational symmetries. That's a finite group, and that group acts on the faces, the set of faces of the dodecahedron, or on the set of vertices or on the set of edges. So that's the kind of example I have in mind here. And if we take any old x in our set X, then the Orbit-Stabiliser theorem says that the size of the group G is equal to the size of the orbit of X times the size of the stabilizer of X. So if we think about our example of this dodecahedron and think about the group of rotational symmetries of the dodecahedron as acting on a set of faces, if I pick a face, say this one, then the orbit of that face is the set of all of the faces, including this one, that I can reach using elements of the group acting on this. So in fact, in this case, we can get from this face to any face, so the orbit is the whole set of faces, but it might not be. That's only because the action in this case is transitive. And then the stabilizer of this face is the set of rotational symmetries, the set of elements of the group that fixes this face. So in this case, I can do rotations like this, for example, all of which fix this face. And that's the stabilizer here. So how are we going to prove this? So the idea is that we're going to define a bijection from the set of left cosets of the stabilizer of X in G to the orbit of X and use Lagrange. So let me write down a little bit about that. So I want to define a map F from the set of left cosets of the stabilizer of X in G to the orbit of X. So the stabilizer of X is a subgroup of G, but it doesn't have to be a normal subgroup of G. So we're not thinking of this as having group structure, it's just a set of left cosets. And then the orbit of X is just a set. So this is a map between sets. We're not looking for any kind of group theory type structure here. And my plan is to show that we can write down a suitable map F that will be a bijection, which tells us that these two sets have the same size, and Lagrange's theorem tells us about the size of this quotient, this set of left cosets. So I'm going to take a left coset G stab X and send it to somewhere on the orbit of X, and the natural place to send it to is whichever element of the set capital X little x gets sent to by the element G when it acts on it. So now we need to show that this map is well defined because it's defined on a quotient. So there's this possibility that we pick different representatives of the same left coset, and then we need to know that they get sent to the same place. So let's see why that's true. So if G1 stab X is equal to G2 stab X, so if I've got these two ways of writing the same left coset, then G1, well, G2 inverse G1, let's say, is in the stabilizer of X. That's by our coset equality test. So we have a criterion that says when two cosets are equal. So what does it mean to be in the stabilizer of X? It means that this element of the group, when it acts on X, gives back just X. And now if I have G2 acting on both sides, I discover that G1 acting on X is equal to G2 acting on X, using the group action property to unravel this. So either way, we end up in the same place in the orbit of X. So our map is well defined. We also want to show that it's a bijection, so let's show first that it's injective. So if G1 acting on X is the same as G2 acting on X. So if I have the same thing on the right hand side here, then G2 inverse G1 acting on X is just X. This is sort of the reverse of what we did up here, which means that G2 inverse G1 is in the stabilizer of X by the definition of the stabilizer of X. So again, we've got this coset equality criterion, and we discovered that the left cosets of G1 stab X and G2 stab X are the same. So if I end up in the same place on the right hand side, I came from the same place on the left hand side. So it is an injection. And you'll see these are kind of reverses of each other, but I wanted to be really clear, but this direction is showing it's well defined, this direction is showing it's injective. And then we also need to show that F is surjective. Well, why is that? So if I take something in the orbit of X, that's going to be of the form G acting on X, well, then that's equal to F applied to this coset G stab X. So it's certainly in the image of F. So our map here is a bijection, and these are finite sets. So the size of the orbit of X is equal to the size of this set of left cosets, the index of the stabilizer of X in G. And we know by Lagrange's theorem that that's equal to the size of the group divided by the size of the stabilizer. Job done. So we can use this to deduce things like, for example, computing the size of this group of rotational symmetries of the dodecahedron, because if I pick a face, I can find the size of its orbit and the size of its stabilizer, and by multiplying I discover the size of the group of rotational symmetries. It also shows useful things like the size of the orbit divides the size of the group. So we already know from Lagrange's theorem that the size of the stabilizer divides the size of the group. This gives us more information, which turns out to be very helpful.